So in the nephron, we have two parallel flows of fluids, and that place where we start having two parallel flows of fluids is with the beginning of filtration in the glomerulus. So one of the fluids is blood. So blood comes into the nephron through the afferent arteriole and goes into the glomerulus. Here in the glomerulus, depending on the blood pressure of the glomerulus, which creates the hydrostatic pressure in the glomerulus, you will either push more water out of the blood and into the tubule or less water. And that is controlled by, if you want to get rid of a lot of water because blood pressure is too high, you would vasodilate the afferent arteriole. If you want to get rid of less water because blood pressure is too low, you would vasoconstrict the afferent arteriole. So to whatever degree of hydrostatic pressure you have, that's going to be the main thing that affects how much water leaves the blood and goes into the tubule. This is the proximal convoluted tubule. And right at that point, you now have two fluids. One is filtrate, one is blood. So the flow of the filtrate shows nicely on this part of the model. Here again is the glomerulus, which is the same as this, only it's way smaller. And so the filtration that I just spoke about that created the filtrate occurred here on this part of the model, and it's occurring here at the glomerulus on this part of the model. So that filtrate will first go into the proximal convoluted tubule. Proximal means it's closest to where you created the filtrate, to the glomerulus. And convoluted means it's all kinked up and coiled up. And the proximal convoluted tubule is up in the cortex. Then it dips down into the medulla. You have the loop. Then it comes, and notice the nephron loop is straight. It is not coiled up. Then it comes back up into the cortex, and it's the distal convoluted tubule. They should have shown this more kinked than it is, but they didn't.
And you showed you'll label like the kinked one on the black.
On the other model, because
Okay.
they've shown the distal convoluted tubule more kinked there. And then the filtrate moves into the collecting duct. Whatever is still left in the filtrate at the end of the collecting duct will drip out of these little papilla into the minor calyx, and now it's urine. And whatever is in the urine at this point will be in the urine when it leaves your body. You can no longer change the contents of things once it's in this place. However, all the time that the filtrate is moving through the proximal convoluted tubule and the nephron loop and the distal convoluted tubule and the collecting duct, it is completely surrounded by these blood vessels. And all of these blood vessels up here and up down here collectively are called the peritubular capillaries. The ones that are down in the medulla that are very straight are also often referred to as the vasa recta. Vasa means blood vessel and recta means straight. So every little teeny weeny bit of the tubule is completely wrapped around with parts of the peritubular capillaries. And so as the filtrate moves through the various parts of the tubule, whatever you need to return to the blood to have perfect blood chemistry, you will reabsorb out of the filtrate and back into the blood. Whatever you need to get out of your blood in order to have perfect blood chemistry, you will leave in the filtrate, and it will ultimately drip out of the papilla, become urine, and leave your body as urine. So this is the nephron. This whole tubule, as well as the blood vessels wrapped all around it, are the chemical processing plant where you're perfecting your blood chemistry by either moving good stuff out of the filtrate and back into the blood, or leaving bad stuff and not reabsorbing it and leaving it in the filtrate. The last little adjustment possibility you have is there are some things such as urea that after you consider how much of that urea went through the filter and left the blood and went into the filtrate, minus how much of it was reabsorbed from the filtrate back into the blood, you end up with too much urea in the blood. and then you can actively secrete the urea using ATP to actively pump it out. That secretion occurs mostly in the distal convoluted tubule and the collecting duct. Another thing that you usually need to secrete is H+, because you usually have too much acid in your body, because you're always creating acid whenever you create carbon dioxide, because carbon dioxide plus water makes carbonic acid. And another thing you usually have to get rid of is potassium ions. And so those are all things that you tend to secrete in the distal convoluted tubule and the collecting duct. Other things that we could talk about in this model, this part of the model here. So perhaps can you hand me that? Let's talk about the flow of blood to get to this part of the model, and then we'll talk about the other blood vessels in that part of the model. So you have blood coming in the renal artery, which is a direct branch off the aorta. The first level of branching are called segmental arteries, and one of these goes to the papilla end of each of the lobes. The segmental arteries then split into two interlobar arteries that go between this lobe and this lobe. The renal pyramids with the immediately surrounding tissue and blood vessels, each one is called a lobe. So this is an interlobar artery and vein, and this is another interlobar artery and vein, interlobar meaning between two lobes. The two interlobar arteries and veins then join and form the arcuate artery and vein, which are very significant because they are marking the boundary between the cortex on the outside and the medulla on the inside.
And that is this part right here.
Yes. And so branching into the cortex off of the arcuate artery and vein are the cortical radiate artery and cortical radiate vein. So then let's leap over to here, and on this microanatomy part of the model, you can see a teeny bit of the arcuate artery and vein right there. Then you can see the interlobar artery and vein. Oh, I'm sorry, this is not arcuate artery. You can see it. You can see very clearly the interlobar artery and vein, and then you can see very clearly here the arcuate artery and vein.
Arch.
It's an arch, and it's the boundary between cortex on the outside and medulla below. And then you can see very clearly the cortical radiate artery and vein radiating out into the cortex. And so the blood flow into the nephron starts from the afferent arteriole, which branches off the cortical radiate artery, and ends when the peritubular capillaries dump back into the cortical radiate vein. The blood flow from this to this is the blood flow through the nephron. And that was afferent arteriole to glomerulus to efferent arteriole to this whole peritubular capillary bed. And at the end of the peritubular capillary bed, this nice purified blood dumps back into the cortical radiate vein, which will then go to the arcuate vein, to the interlobar vein, back to the renal vein. Thank you, ladies, for putting that away.
And then on that other one, what would you label on the?
On this?
No, on the other.
On this guy.
Yeah.
So this is corresponding to that model, and things in this middle part that are nicely shown on this model. So I might label them on the practical. Here's the glomerulus, the glomerular capsule. Here's the proximal convoluted tubule. Here's the loop. Here's the distal convoluted tubule, the more bright green. Here's the collecting duct. On this nephron, they showed the capsule, the proximal convoluted tubule, the loop. They failed to show the distal convoluted tubule, but they do show that these two nephrons are both dumping into this collecting duct. As far as blood vessels go, here's the arcuate artery and vein, which are showing you the boundary between cortex out here and medulla down there. Here's the cortical radiate artery and vein, which are very well shown. And you can see afferent arteriole leading to glomerulus. This cross-hatching is not at all what the peritubular capillaries look like. They look more like this, so I wouldn't label this. This vasa recta is not bad. I could possibly label that. So basically, anything on this
Besides the crosshatch.
other than the crosshatch, I could label.
And then on the,
On this, the same things on both of these. See you Wednesday. This would be afferent arterial. That's part of the juxtaglomerular apparatus where it has measuring devices to measure the blood pressure in the afferent arterial to decide whether you need to vasoconstrict or vasodilate. This would be the afferent arterial in this model. This would be the efferent arterial. This would be the efferent arterial in this model. This whole cluster and this whole cluster would be the glomerulus. Here is the naked capillaries of the glomerulus. And then the part that's showing you gray is showing you where the visceral layer of the capsule is adhered to the outside of the capillaries. So the filtration membrane that anything has to pass through to get out of the blood and into the filtrate has to pass through the wall of the capillary, the visceral layer of the capsule, which is made up of podocytes, and this model shows the individual podocytes with their little foot processes, and then their little filtration slits in between. So gluing the podocytes onto the capillary is the basement membrane. So anything that wants to leave the blood and get into the filtrate has to pass through the wall of the capillary, through the basement membrane, and through the filtration slits between the foot processes of the podocytes. So any of that I could have questions related to. This is the parietal layer of the capsule, which was the simple squamous epithelium that we looked at in the slide in 201. This is the proximal convoluted tubule made up of simple cuboidal epithelium. We looked at that
today.
Today and also in 201 as a sample of simple cuboidal epithelium. This is the distal convoluted tubule, where you have the macula densa, right where the loop meets the distal convoluted tubule. So in this model, this is the distal convoluted tubule with the macula densa. That would be the proximal convoluted tubule. In this model, the red is the capillary without the visceral layer of the capsule on it. This tan stuff is representing the visceral layer of the capsule. These little squiggly lines, I think, are representing the filtration slits.
But you preferred on the other one
I like it better on this one.
because it shows the hepatocytes.
You can see the podocytes and see the foot processes and the slits between. Yeah, so those, any of that stuff I could label on either of these models.
Okay, thank you.
You're welcome.